Okay, so as we said here, in truncation error, larger is the terms we keep, lower will be the truncation error. And let us take we will take some examples on how to develop a function around a certain point using truncation methods. So first, for example, if they ask us to use Taylor series to expand sin x about x equals 0, okay? What we will do is we will just apply the formula, okay? We start by sine of x, which is the function to expand around 0, is equal to, you know that the general relation is f of x, which is here sine of x, is equal to f at a, here a, the point we are expanding about is 0, plus x minus a, here a is 0, so x minus 0 times the first derivative f prime at point 0 over 1 factorial, okay? And 1 factorial is 1. Now, what is f prime? We should perform the derivative. So we have f of x is equal to sine of x. So if we perform a first derivation, we derive a first time, we get that f prime x is equal to cosine of x. So now, by replacing f prime at 0, it's cosine 0, plus, we continue the expansion, so plus x minus 0 square now, so it's x minus a square, over 2 factorial, which is 1 times 2, it's 2, times the second derivative of function f at point 0. So now we should continue the derivation here. If we continue, we have f second at x. The derivative of cosine of x is minus cosine of x. So it's minus cosine of x, sorry, minus sine of x. Okay. And now we just have to replace here by minus sine 0. Now, if we continue, f third of x is the derivative of minus sine x is minus cosine x. You will see now, if you continue, you will see that we have a repetition. Because if you derive again, okay, if you derive f fourth, the fourth derivative with respect to x will be sine of x, because the derivative of minus cosine is sine. So we have now a repetition. So the periodicity will be as follows: sine x, cosine x, minus sine x, minus cosine x, and it will be repeated again. Sine, cosine, minus sine, minus cosine. When we have periodicity, this will simplify the problem. We will have like a repetitive pattern. Okay. So for example, here, in this case, you have cosine 0 is 1. You have sine 0 is 0. Okay. So whenever you have for any order, so here you have f second, okay, and f fourth, sine of 0. So for even numbers, 2, 4, 6, 8, 10, etc., the terms will be cancelled out because you are multiplying by sine 0, which is 0. So you will only end up with odd terms, okay, and the sign will be alternating. Why? Because, for example, f prime will be plus cosine x, while f third will be minus cosine x, and f to the power f fifth, 1, 2, 3, 4, 5, will be plus cosine x, and it will be repetitive. So you will have alternation, you have alternating sign from plus to minus. So here, if you look at it, even exponent will be cancelled out, because for all even exponent, x squared, x4, x6, it's multiplied by sine 0. or minus sign 0, but both are 0. And I will be left only with odd coefficient. So it's with alternating signs. So it's x to the power 1 over 1 factorial, but 1 factorial is 1. Now I will continue the series in a repetitive way. So minus x3 over 3 factorial plus x5 over 5 factorial minus x7 over 7 factorial, etc. Okay, so the pattern is repetitive with alternating signs. Now, if I want to model sine of x, I can do it in several ways. It depends on what is the number of terms I want to keep and what is the number of terms I want to eliminate. If I just want to stop at x equal at an exponent x5, then I will neglect all term after x7, and my truncation error will be equal to this summation from x7, so from minus x7 over 7 factorial to infinite other terms. Now, if I decide to keep, let's say, 5 terms, 1, 2, 3, 4, 5, and I will do my truncation here, then my truncation error will be reduced, okay, because I will neglect now a smaller number of terms, okay? And now we can see this by drawing the function, the actual function sine x, and drawing the different functions. So if I do truncation here, I can approximate sine x by x. But you will see that this approximation is only valid if x is very close to 0. Because when you take more terms, your approximation will be valid for a larger interval, since your truncation error will be reduced. We will see this in the following slide in the graph. So if you look at your graph here, okay, in this graph, you are representing sine x in different ways. First, the white line is the exact presentation of sine of x function. So this is the white line representing sine of x. Now I will use different approximations. First, I will say if I just take the first term, if I just take x, it's just a linear variation. And if you compare on your figure, you can see that this approximation is only valid in this zone, in a very limited zone, because as I go far from 0, the difference with the white curve will increase. Okay, so I will get larger and larger errors. So I can say then that this approximation will nearly be only valid between maybe -1 and 1 nearly, and after this it will not be accurate anymore. While if I take 2 terms instead of 1 term, if I do the truncation at this level, if I represent x minus x3 over 3 factorial, I will get the yellow curve. So this is represented by the yellow curve. And if you compare now, I will just clear a little bit so that you can see it in a clearer way. If you look at the yellow curve, it's more matching. هلا look, الred curve اللي مرسومة آخر شيء هي if we take all terms, and you can see that this is why the red curve is matching a lot with sine x for a high interval. يعني if you compare the red and white curve, nearly they start to match from this point nearly. From this one to this one. So by taking all of these terms, you can compute accurately sine of x from nearly -5.5 to plus 5.5. You will nearly have the same value for both. So the error will be very small in this range. Okay? So you can see that higher is the number that I can take into account, then the approximation can work for a larger interval. Okay? So now, if you take the yellow curve, it's better than the linear approximation. So you can start to see a difference from this point, which is nearly at nearly at 2.5. Okay, so instead of just having from -1 to 1 a good approximation, by taking two terms, we can have good approximation from -2.5 to +2.5 nearly. Okay, so until here nearly. Okay, so you can see that by taking more terms, the interval for which I have accurate results is higher, and the round of error will be acceptable for a larger interval. So now, if I move now to take, instead of just two terms, three terms, okay, then I have the presentation through this line. And also, as you can see, the interval of accuracy will be increased also. So I am increasing the interval of accuracy as I am taking more terms. And if I take x7, now I go to the green line. So this is the representation, the green line. So for the green line, for example, also you have the point where I start to see a difference is this one, nearly. So nearly 4, okay? And of course, from the other side, it's symmetrical with respect to x. So from the other side also, it will be nearly -4. And now, taking 1, 2, 3, 4, 5 terms into account, then I will move to the blue curve, okay? And larger, I can have larger and larger interval of accurate values. And the most accurate one will be to take all these terms. Of course, I can be more accurate if I continue, and I will take now, if I continue with plus x to the power 13 over 13 factorial, etc. Higher is the number, and if I take a very high number, I can end up with a good match for a very large interval. Okay, I can end up with nearly having the same function, but I need a very large number of terms to take into account. Okay? Any question on this? So now, let us see in this example, also here we forgot to put the minus here. Look, all typing errors, I will fix them before posting on Blackboard, okay? Everything will be fixed for you on the final PDF on Blackboard. So sometimes we forget to put some details. So here we want to use Taylor series to expand exponential minus x about x equal to 1. So it's similar. It's a similar approach. So any function we give, we can do for it Taylor series expansion. So just we have to apply the formula. So here, let us do it again. So the function to expand is exponential minus x. So this is f of x. It's equal to f at the point of interest. So f at 1, okay? The point we want to expand about is x equal to 1. So if we replace in the function, f of 1 is exponential of -1. So we have exponential -1 plus, now we have x minus a, so we have x minus 1 times the first derivative at point at 1, okay? At x equal to 1. So for this reason, we should do the derivative. So here also you see that it's a repetitive series because you have f of x is exponential minus x. So if you derive the first time with respect to x, you will get that f prime of x is minus exponential minus x. And if you continue, you will see that you will have repetition. And the repetition here is the periodicity. Each two terms it's repeating. In the above example, each 4 terms it was repeating. So I have f second of x minus minus will give me plus, and I will go back to exponential minus x. And it will be repeated in an infinite way. So it's a periodic derivation. Okay? So as you can see, all derivative of order that is odd order, yani first derivative, third derivative, fifth derivative will be minus exponential minus x, and all derivatives that are even order, so f to the power here, this is the first value, so the second derivative, f to the power 2, f to the power 4, 6, etc., will all be equal to exponential minus x. Okay? So now, if I replace in my expression, I will get exponential minus 1 plus x minus 1 minus exponential minus 1 plus. So here you will see that what will happen is that the sign, okay, will vary, because here you have the derivative is minus exponential minus 1, while for even numbers the derivative is positive. Okay, this is why you will end up with a negative sign for odd exponents, and you will have a positive sign for even exponents. Okay, so as you can see here, you will have a repetitive pattern. So it's first 0.36788, which is exponential minus 1, minus 0.36788x minus 1 plus 0.36788x minus 1 square over 2 factorial. Now, if we want to continue, it's now minus, so it's minus 0.36788 times x minus 1 to the power 3. So for all odd numbers, odd coefficients, it will be a negative sign, while for even coefficients, it will be a positive sign. So now plus 0.36788 times x minus 1 to the power 4 over 4 factorial, and it will be repeated. Okay, it will be repeated several times. So now, if we consider the error induced, okay, we want to compute around 1. So we can take, for example, 1.25. If you want to compute what is f 1.25, the exact value, we can calculate it, because we know that f of 1.25 is equal to exponential of minus 1.25. So we can easily get the exact value. أكيد if you use a calculator, you will get a certain value with a round of error, but if you are using a calculator of high precision, you can nearly be very close to the exact value of exponential of minus 1.25. And you want to compare with the result you get from Taylor series expansion. So if you are using 3 terms in the series, f of 1.25 will give you 0.2759096. And if you use 4 terms, the value obtained will be 0.2864478. Now, using the calculator or a high precision equipment, you can see that nearly the exact value is 0.2865048. So now you can compare. Okay, you can find what is the induced error. In general, for example, we have several types of errors that we will introduce now. You can just find the true error if you want, which is the difference between the values. So if you do for 3 terms, let's say, if I have 3 terms, if I do the difference between these two, I can find what is the error induced. And I also can calculate the error in another form. I can calculate it using a relative approach, and we will introduce this when we talk about the ways of representing an error. So in this way, you can find what is the errors, if you want, the true error induced, which is the difference, or the relative error induced, which is a percent error. Okay. So here, for example, by just doing the difference, you can see that when you increase the number of terms, you will be able to reduce your error. Okay? Because look here, you have a high match between these two values because nearly the first, so here you have the first three numbers after your comma are the same, nearly the same. Okay, so when you subtract, we'll have that the error is of order of 5.7 times 10 minus 5, which is pretty good. Okay, while if you just take three terms, then you will start to have difference starting from the second point after the digit. Okay, so its second number after the digit is different. This is why here when you subtract, it's of the order of the 10 minus 2, 0.01 something. Okay. Now, we will define what is the main types of errors that we can encounter. So we have several types that we can define. Okay. First, we have the true error, and we use the true error in case we know the true value. What is the value of the error? Because what is the value of the number we want to approach? Okay, because last time we introduced numerical techniques, we said that in many cases we don't have the exact solution. If I don't have the exact solution, this is why in general I use numerical methods, because I don't know what is the exact value. So in general, this type of errors is not very common, because when I use numerical methods, this means that in general, I don't know the exact solution. Okay. But in this course, in order to understand how numerical methods work, we are taking first examples in case we know the exact value and we want to compare with numerical techniques. So in this case, if you know the exact value and you are doing numerical methods to try to approximate it, then you can calculate the true error as the difference between the true value and the approximate value. So for example, if we go back to the previous example, we can do this. So if we go to this example here, if you want to find what is the true error involved using three terms in the series, you can just say that E true, when I take three terms, will be equal to the true value, which is the exact value, which is here. So it's 0.2865048 minus the value I got from computation, which is 0.2759096. Okay. Now, if you are interested into finding another type of error, which is the relative error, okay. First, the notation is as follows: capital letter is for the true error. It's not a percentage. It's not relative. While for relative error, it's a lowercase. So we put it like this. It's like an epsilon. So epsilon true is equal to the difference between the exact and value we got from numerical analysis. So if you want, it is equal to the error, the true error, over the exact value. So in this way, and this type of error is more, if you want, is more representative. You know why? Because let's say I tell you I did a measurement and the error is 1 millimeter. It might be very good, it might be very bad, because I don't know what is the exact value. I should have a knowledge about the order of the exact value to know if 1 millimeter is fine or not. And for example, if I take a house and I measure the dimension here, this length, let's say this length is 10 meters. 1 millimeter compared to 10 meters is an acceptable error. But if I'm just measuring a small object for which the side is 1 centimeter, and I tell you the error is 1 millimeter, it's bad. So this is why in general, we prefer to work with relative errors, or also we call them percent errors, because they can give us an estimate of the error relative to the exact value or to the approximated value. Okay, But also sometimes we say that it's good to know also the error, because it will tell us the number, the margin, the interval we are working in. So what is the margin of error we can have? Okay. So they can ask you for several types of error in problems. They can ask you to calculate the true error. They can ask you to find the true relative error. Now, as we said, sometimes we are not able to calculate the true value. So if we have a problem where the exact solution is not known and we can only solve it numerically, if we want to get an approximate relative error, okay, then we should, if you want, base ourselves on something else. And what we do in this case is that we know that in numerical techniques, we get the solution by iterations. And we expect, if our solution is converging, that higher is the number of iterations, okay, we will tend to reduce the error. So in this way, we can define, based on the iteration, a certain method for approximate relative error. And this method will just take into consideration, when you do iterations, the value that you get, the final value that you get from the final iterations, minus the value that you had from previous iteration over the new value you are getting. So this will give you an approximate relative error. And also you can get a certain, as we have big capital E true error and small e okay, small e true, you can have the same for approximate. So instead of giving it as a percentage, you can just do the difference. It's also possible in case of approximation. Okay, so and in general, we give the error an absolute value, because we don't care for the sign, if it's positive or negative. We just can give it as absolute value, and it will give you the maximum. It will give you the maximum possible error that is induced in this operation. So here, for example, if you want, in the previous example, to assess what is the approximate relative error, we can do the following. Going back to the previous example, you can compare iterations. So if you take 3 terms and if you take 4 terms, so these are 2 iterations. You can compare these two. So you can say, this is the number I obtain if I include 3 terms. This is the number I obtain if I include 4 terms. So I can consider that this is V new and this is V old. Okay. And then in order to calculate the relative approximate error induced, I can do V new minus V old over V new. In general, we set a criterion to stop. We say, for example, I will stop iterations when the approximate relative error becomes lower than 5%, for example. So you can test here if your result, you compare with 5%. If it's smaller, then you stop. If it's higher, you say, no, I want to continue to have more accurate results. And this criterion can be varied. Okay, it depends on what is the accuracy you desire. If you want a very high accuracy or not. Okay, or here, for example, let's say when they perform the calculation, in case you say, in terms of error, I want to stop at 10 minus 4, let's say, and you have calculated for 3 terms, this is the induced error. For 4 terms, this is the induced error. Then, since 5.7 times 10 minus 5 is smaller than 10 minus 4, I can stop here. Okay, so it depends on which error you are considering and which criterion you are taking. And you can base yourself here. You can base yourself on true error. You can base yourself on approximate error. Here, both are possible because you know the exact solution. But in cases where you don't know the exact solution, you should deal with approximate errors in this case. Okay? Any question on this? Okay. Now, we will go to derivatives using Taylor series expansions. We will consider continuous and discrete space. So we had tackled this in the previous session if you want. Now we will summarize our findings again. So we talked that when we want to work numerically with the derivatives, when we deal numerically with derivatives, we should work in discrete domains. So instead of taking a continuous curve, I'm just working at discrete points. Okay, so I will discretize my domain, then I will select a certain step, delta x, h is equal to delta x, and then I can number my discrete points. So if I consider, let's say this is x of I, then the point just before can be written as x minus 1, and the one before it is x minus 2, and the ones after it are x plus 1 and x plus 2. And I will use these points to define derivatives in several ways. And we have seen together last time that we can approximate the derivation in several ways. We can take into consideration if we have point I, let's say, and it's surrounded by point I minus 1 and point I plus 1. We have several options to write the derivative. When we say delta f over delta x, we can take point I with point I minus 1. And then we can write delta f over delta x as fi minus fi minus 1 over xi minus xi minus 1. This is called, if you remember, this is the backward scheme. So this is the backward scheme. Now, if I take I with I plus 1, the expression will be fi plus 1 minus fi over xi plus 1 minus xi. This will be the forward scheme. Okay, and finally, if I take the point before and the point after, it will be fi plus 1 minus fi minus 1 over xi plus 1 minus xi minus 1. This is the centered scheme. We will see together that these expressions are derived from Taylor expansion series. Okay, last time we just introduced them, but we didn't mention how we got these expressions. We will see here how we come up with these expressions of derivations. So the idea is to start from Taylor series expansion. So let's say I want to use the forward method. If I want to use the forward method, I will try to expand f of x about xi, and then I will replace x by xi plus 1 to find what is the expression of fxi plus 1, function of fxi, and the derivatives. Okay, first, second, third, etc. If I do this here, we know that from Taylor expansion, fx is fxi plus x minus xi, f prime xi, etc. Now I will just replace x in the Taylor expansion by xi plus 1. And if I observe my result, and I replace delta x, which is xi plus 1 minus xi, by the increment h, then I can write fxi plus 1 as follows. It's fxi plus hf prime xi plus h squared over 2 factorial f second xi, etc. Now, what is interesting for me here is to come up with an equation for the derivative of f prime at xi. And to do so, I will take this term to the other side, and I will take fxi plus 1 to this side, okay? And I will rearrange terms, so I will divide by h to get the expression of f prime function of the other parameters. If I do so, okay, what I will obtain is the following. So I just exchanged the place of terms in a way to get f prime xi function of the other parameters. Okay, I will get the following. F prime xi will be equal to fxi plus 1 minus fxi over h minus h over 2f second x minus h squared over 6f third of xi, etc. Okay, because if you just remove this term to this side, you remove all terms to the other side, and you divide by h, you will get what is f prime xi. Or you can take f prime xi to the other side, it will be minus f prime xi, and then you put minus for all terms to get f prime xi. So it's very simple. You can do several approaches just to get what is f prime xi. Once you get this development, you will try to neglect terms that are small compared to others. So here, what we are doing, we are dividing delta f by h, and already you know that in general, when you do an approximation for the derivative, you will try to take h small, because the definition of derivation is to take the limit as h tends to 0. We will not take it 0 because it will not be definite if we take here h 0, but we will take it very close to 0. Okay, and if we take it far from 0, then we expect to start to have errors. Okay, so since h is small, so to be accurate, h should be smaller than 1, and h is multiplying here. So here I'm dividing by h, which will give me a high number here, while for the other terms I am multiplying here by h, I am multiplying by h squared, by h cubed, etc. Then I can say, because h is small, this term will be dominant over all other terms, and it will be much larger than h over 2f second of xi, which will be much larger than h squared over 6f third of xi, etc. So what I can say then is that my error will be of the order of this term, because the larger term that I will neglect is this one. So my error will be of the order of this term, which is order of h. Okay, so we say then that the forward approximation is derived from Taylor series and is expected to lead to an error of the order of h. This is why smaller will be my h, higher will be my accuracy, and lower will be my error. Okay, now of course I just have the assumption that I am working with finite numbers here, yani f second, f third are not infinite number or very large number to have this result. Okay, now I will do the same procedure for to derive the expression of backward derivative. So when I use the concept of backward scheme, I will use the same approach, but now instead of developing fx, instead of taking fx plus 1, I will take, instead of x, fx minus 1, in order to get a relation between fxi minus 1 and the derivative. So it's exactly the same method, but I replace x by xi minus 1. And when I do so, I am interested into finding the expression of f prime at xi. So also I will take terms, all other terms to the other side. And since the increment is constant, is h, so I can replace xi minus 1 minus xi by minus h. Okay, and then what I will get now, I will get an expression for f prime by rearranging my terms. I will get the following expression. Using exactly the same approach, I can come up with f prime xi function of